Hi there, a quick video to show what analysis and thinking process we can go through when we have an electrical circuit and we have circuit theory and the measurements on a real circuit that we've got here. Coil L 47 millihenries, resistor 270 ohms connected in series. When the circuit measurements don't match the theory, what logical process can we go through to understand exactly what is going on? So what we've got here is a circuit. We've got a signal generator, 400 hertz, 20 volts peak to peak, can be seen on the oscilloscope, 7.07 volts RMS, 47 millihenry coil, inductor, 270 ohm resistor, so it's a simple series circuit. So what we've got from circuit theory is, if we use circuit theory, first thing we need to do is to work out the opposition to current flow from the inductor, XL. 2 pi FL, we're using a frequency of 400 hertz, that's aircraft frequency, works out to be 118 ohms. This is two-dimensional computation, it's magnitude and phase angle. The phase angle of XL is 90 degrees with respect to the resistor. So to work out the circuit impedance, the opposition to current flow for the actual series circuit with R and L in series, we have to use Pythagoras, and it works out to be 295 ohms. From that 295 ohms, we can predict from Ohm's law, V divided by Z, that we should get out 24 milliamps. That should be the current in the physical circuit, and on the oscilloscope the phase angle using trigonometry should be 23.6, 24 degrees. Now we can see from the meters that that is not the case, and we can also predict the voltage across the resistor and the voltage across the inductor. So VR across the resistor from Ohm's law, the prediction from circuit theory would be 6.48 volts. The prediction for the voltage across the inductor would be 2.83 volts. And as a sanity check, those two voltages are 90 degrees out of phase. So if we do Pythagoras right angle triangle on them, we should get back to the 7.07, and these are RMS values, root mean square, that we apply to the circuit. So we can see from this circuit that we don't have 24 milliamps, we only have 14 milliamps flowing in the circuit through this current meter. We have 3.91 across the resistor. Now the prediction was 24 milliamps from circuit theory. Voltage drop across the resistor, the prediction was 6.48. Now what if we want to get the voltage across the inductor? We can swap these two components over without moving anything else, and the prediction was 2.83 across the coil voltage, and what we get here is 2.83 if we get the voltage across the coil. That current hasn't changed. So the voltage across the inductor appears to be correct, but the voltage across the resistor is way out and the current is way out. So there is something amiss in the circuit. So the measurements are, that was 2.83, and if we go back, put across the resistor again, go across the resistor again just to check the actual readings, what we're getting is VR is 4.04. So we can see these are the actual measurements in the circuit. So the measurements, apart from VL, do not match the theory. So exactly what is going on. And also what we want to check is the phase shift on the oscilloscope as well. So to work out phase shift, we use the time between the waveforms. So on the oscilloscope screen here, we've got the voltage going in, which is the bigger amplitude, and the voltage coming out. We can see that they do not cross the zero axis at the same time. They don't reach their peaks at the same time, so they're phase shifted. So how can we tell the phase shift? If we go down in time base to 0.1 milliseconds per division, what we can see is, we just move that along a bit, then we have 1.6 divisions between the waveforms, phase difference in time. So if we do 1.6, that is 1.6, it's 0.16, so apologies, it's 0.16, 0.16, well that's out. So we've got 0.16 divided by 2.5 milliseconds. So we need to do this calculation for the phase shift. We take the time, which is 0.16 from the oscilloscope screen, and we divide it by 2.5 and multiply by 360. And if we do that calculation, we'll get a phase shift. So we've got 0.16 divided by 2.5 millisecond cycle time, and then multiply that by 360 degrees. We get a phase angle of 23 degrees. You get a phase angle of 23 degrees on the oscilloscope. Now that's fairly close to the prediction, which was 24 degrees. Not quite exact, but it's not far off. So the biggest one, that's the two measurements in the physical circuit that are significantly different is the circuit current, which is 10 milliamps out, and the voltage across the resistor, which is more than 2.5 volts out. So there's something amiss in this circuit that doesn't quite match up to the predictions from circuit theory. So what can we do to get to the root and understand what's going on? So what we can do is we can take the resistor out of the circuit. So we can take the resistor out of the circuit and we can measure the resistance of that. We can measure the resistance of the resistor. So we put the leads together. We're not getting a very good connection there. Put the leads together to measure 0. Okay, 0 ohms, and then either side of the 270 ohms, connect it on with a good connection. It's nominally, yes, good connection is required with the leads. It's nominally 270 ohms. Let's see, yep. It's nominally 270 ohms, and we measure 266. So that resistor, it would, from measurement, that resistor within tolerance is the nominal value of 270 ohms. It's only slightly out, it's only a few ohms out with tolerance. Okay, so that doesn't seem to be an issue. However, what if we take the coil out? Okay, so we can measure the wire, we can measure the resistance of this coil, and the resistance of the coil is ideally should be 0. So from circuit theory, using circuit theory, it assumes you've got 0 ohms through this coil. But on a physical circuit, you're never going to get 0 ohms. On this circuit, put it down onto the 200 ohms range to get it more accurate. What we've got here is 128 ohm actual opposition to current flow simply from the length of the wire and the cross-sectional area of the wire. That is significantly different to 0 ohms. So the circuit theory uses 0 ohm resistance for the inductor. In the physical circuit, it's actually 128. So that explains why the current is so significantly different, and the voltage across the resistor is significantly different to circuit theory. So through analysis, through a bit of measurement, we can work out exactly what's going on. So why would this be 128 ohms? Well, this is a tiny coil. You can actually see the footprint. It's got a diameter of less than 10 mil. So the wire inside is going to be hair thin. So its actual resistance is going to be quite high. And we can measure it as 128 ohms. Okay, hope that video has been useful to do actual physical measurement and to work out if the measurements don't match circuit theory exactly what is going on. Thank you for watching.